Good afternoon. So today we have another topic that should take probably more than 50 minutes worth of your time. So typically covered in 2 regular class meetings. Not because the method itself or the topic itself is overly difficult. If you have the patience to go through the whole thing, you'll see at the end of the lesson that conceptually speaking, it's actually not that difficult. It's just an algorithm of how to integrate a specific type of function, which you see already written down here. So by the way, you can pause the video and take your time to write this down. But some of the preliminary stuff that I want to describe or to talk about before we get to the actual examples, these preliminary items will take usually more time than usual. So they are a little bit tedious to write, so that's why it may take a little bit more time. And I should emphasize this is another topic in which the goal is to understand the algorithm or the overall method, to be able, secondly, to be able to do in a relatively short amount of time simple versions of these types of problems, because the slightly more complicated ones, we don't usually do them by hand because the process may take much longer than it's worth doing it on paper. So one can use, of course, computer algebra systems, and I'm going to show you actually a couple of examples as an addendum to this lecture, with a Maple presentation or something similar, maybe with Wolfram Alpha, we'll see. But it's very important to know the overall algorithm behind it, because even if you use a computer algebra system, you need to be able to understand if what you see is actually correct. And another very important thing related to this class is that in other courses that you'll learn later, like differential equations, when you learn something like Laplace transform, and many other formulas are given in terms of so-called partial fractions that I mentioned here. So you need to know what this what this means and how it relates to rational functions. So again, with patience, remember, I don't believe in going too fast if you really want to learn a topic. Let's start from scratch with the goal. Okay, so we want to integrate or to develop a method to integrate a rational fraction. This is basically a fraction that involves the ratio of 2 polynomials with real coefficients. So on the top you have a polynomial of degree n, on the bottom a polynomial of degree m. Okay, so n and m stand for natural numbers. The coefficients can be real numbers, but n and m are the degrees of the polynomials. And there is a theorem which I will mention later in the lecture, which states that specific types of these rational fractions can be split into partial fractions. And actually any rational fraction can be in fact boiled down to one of those rational fractions that can be split into simpler, relatively speaking, partial fractions. So I actually want to start with the ending here and describe what we mean by a partial fraction. Once we talk about that a little bit, and then once we integrate some examples of partial fractions, then we're going to get back to see how we can actually decompose any rational fraction into a sum of partial fractions. So the idea is that this big rational fraction, if I can write it into a sum of pieces that can be integrated, then those pieces are partial fractions, and that's the way it goes with this integrational algorithm. So what is a partial fraction? So we have actually 2 types of partial fractions, but even before we touch on that, let me remind you that an irreducible quadratic, so you have basically, if you look at a second degree polynomial, so let's look at a quadratic polynomial, which you're very familiar with because it's involved in many equations, right, of many equations that you encountered so far, the so-called quadratic equation. So if you have a quadratic polynomial, there are essentially 2 types of polynomials of degree 2, those who can be factored further and those who are irreducible. So a quadratic polynomial is irreducible if it cannot be factored. into linear terms, into linear factors. So as an example, x squared minus 3x plus 2 is not irreducible, or it's reducible if you want, because this can be factored. But on the other hand, if you look at x squared, so this is reducible. But if you look at x squared plus 4x plus 5, this is irreducible. No matter how much you try, you cannot actually factor it in real numbers. When I say irreducible, I mean over polynomials or with real coefficients. So a quick test to see if it's irreducible, when you look at a quadratic polynomial, is to look at the discriminant, b squared minus 4ac. If this is negative, then the polynomial is irreducible. The quadratic is irreducible. So notice here that if you check this, 4 squared minus 4 times 1 times 5 gives me 16 minus 20, which is minus 4, so indeed it's less than 0. So that's the fastest way to figure out if a quadratic is irreducible. So keep this in mind, because one part of the piece of the algorithm that we will learn is to actually factor the denominator of this rational fraction. And it's important to know when those quadratic factors that may pop up, when they are irreducible and when they are not. So going back to the partial fractions, we have basically two types of partial fractions. So the first type, let's call it type 1, involves a constant on the top of the fraction and a linear term on the bottom of the form x plus b to the power n. Again, n stands for a natural number, 1, 2, 3, and so on. A and b are just constants, real constants. And by the way, this n is called the multiplicity of the factor or the term x plus b. So again, this constitutes one type of partial fraction. Constant on the top, a linear term on the bottom, raised to a natural number, which can be 1, 2, 3, and so on. These are the easiest one to integrate, and I'm going to show you an example right away. But this is one type of partial fraction that can appear in the so-called partial fraction decomposition. Again, the key thing and why we bother to go about this story is that partial fractions can be integrated. Some of them very quickly, so without too much headache. Others, maybe with some headaches, but they can still be integrated by the methods we actually learned already. So, in fact, let's actually write this as a remark. We know how to integrate partial fractions. Well, we know if we sweat already, as we should in calculus 2 up until this portion of the course. All right, so type 1s are the easiest ones. So here's an example. Let's say I want to integrate 3 over x plus 5 to the power 4. Just the u substitution for x plus 5 will do. It will convert this into a power rule, basically. If that's not obvious already, with a little practice, by the way, you should be able to integrate this directly without writing down an explicit substitution. But if you still don't know what I'm talking about, let's take an extra step here. So we can substitute x plus 5 with u. Du becomes 1 times dx. So then the integral in terms of the new variable u is going to be 3 over u to the 4th dx, which you can write it as a power, du, I'm sorry, not dx. And then using the power rule, this becomes, let's see, minus 4 plus 1 over minus 2, yeah. So 3 over minus 2, that's minus 1, 1 to the u to the negative 1, that's 1 over u. So then when you go back to the original variable, that's minus 1 over x plus 5 1 over, I'm sorry, minus 1 over u to the power 3. Okay, so it's going to be minus 1 over x plus 5 to the power 3 plus a constant c. Let me write it one more time here so it looks better. Minus 3, this one double check. Okay, all right, so that's type 1. Oh, and by the way, I should mention here, let's do another quick example of type 1. And then we'll move on to the second page to the second type of a partial fraction. So all of these involve the power rule when you integrate them, with the exception when n is equal to 1. So if you have, let's say, 5 over, let's say, x minus 3, here's another example. So this is multiplicity 1, basically, when n equals 1. You should be able to do this in your mind, by the way, but notice it's not the power rule, right? If you do the substitution, du u equals x minus 3, which means du equals dx, this essentially becomes 5 over u du. But the integral is ln of u, right? So when you write the answer, that's going to be 5 ln of x minus 3 plus a constant c. So remember not to confuse this case with the power rule, right? When n equals 1, when you have a linear term, the integral ends up in a natural log. So things are easy with partial fractions of type 1. Let's stay tuned for the second page when we deal with partial fractions of type 2. And then after that, we're going to get back to how we do this partial fraction decomposition. All right, so the second type of partial fraction has the form of a linear term on the top and an irreducible quadratic on the bottom of this form, again with multiplicity n. So n again stands for a natural number. So x squared, again, is very important to point this out. X squared plus cx plus d is irreducible. The coefficient of x squared is 1 for reasons that I'll mention later, but it's important to point out it's irreducible, because if it's reducible, it has to be factored, and you'll have basically just a bunch of partial fraction of type 1 when you do the partial fraction decomposition. So it's irreducible, cannot be factored. Which means if you look at the discriminant, that's c squared minus 4 times 1 times d should be less than 0, right? If you want a quick check. So here are a couple of examples. 3x minus 1 over x squared plus 4x plus 5 to the power 3. Let's say you have x plus 3 over x squared plus x plus 1. 3x minus 1 over x squared plus 9. This is also irreducible, and you will see it's easier to handle if you don't have the x in the middle. So if the coefficient of x is 0. Let's see. So yeah, we'll get to more examples later. But for now, I just want to point out how one actually gets to integrate these type of partial fractions. If you look carefully, you'll probably realize that some of them are much easier to integrate than others, although none of them is as easy as the previous one. So we still know how to integrate partial fractions of type 2, but there's a little bit more work involved in doing this. Now, this type of partial fraction that you will encounter in this class will be essentially with factors like this on the bottom, because when you have the x in the middle here, you have to complete the square. There's a little bit more headache, and I try to avoid that in the interest of saving the time. But let's look at the last one, and let's see how one can integrate it if one encounters a partial fraction of this type. So the rule of thumb is usually to split it into pieces. Isolate the piece that contains x on the top. So basically split this into the difference of two fractions. And then integrate each of them term by term. And in anticipation for what I'm going to end up with here, let me remind you another formula, which especially in this section, you should probably write it down on your formula sheet. Because again, if you don't have enough practice, people sometimes confuse this with the natural log, and make sure you don't confuse it. Namely the integral of 1 over x squared plus a squared, and the last term is of this type, is 1 over a arctangent or inverse tangent of x over a. Right, that's one of those basic derivatives. So when we split this integral into two pieces, the first one will work with the u substitution if you look carefully, and the second one is an arctangent with a equals 3. So if you match x squared plus 9 with a squared, a will be 3 in that last part. Here you could do for the first one a quick u substitution. U equals x squared plus 9, du equals 2x dx. So the first integral becomes 3, 1 over u, x dx becomes du over 2. Then the last one is 1/3 inverse tangent of x over 3. So the first one is 3 over 2 ln of u, u being x squared plus 9. And then minus 1/3 inverse tangent of x over 3 plus a constant c. So this is how you handle a partial fraction of this type. Okay, what do you do if you have a partial fraction of like the one in the middle here, like still multiplicity 1, but with x in the middle? Well, things can be a little bit more tricky. And again, this type of example, I'll try to avoid it. In general, I'll avoid it in the exam or quizzes, but in the interest of satisfying the viewer curiosity, let's say, let's actually proceed with a typical example on how you proceed when you have something like that. So let's say I have on the top, let's do one with easier numbers. Let's say I have x plus, let's do x plus 2 on the top, and on the bottom x squared plus 4x. And let's make it really nice. Let's say plus 13. You'll see why that's nice actually. I like to have nice numbers so that I don't have radicals. The method of integrating this, again, this is a partial fraction, right? I mean, you can check the bottom is irreducible, the top is linear. It has to be of that form mentioned here. The approach is kind of similar to the previous case, but we need to complete the square on the bottom. So if you want a quick refresher, completion of the square means essentially going backwards on the formula a squared plus 2ab plus b squared, which combines into a plus b squared. So specifically in this case, you look at the first two terms, you look at the middle term, and take half of the coefficient of x and square it. So that makes it 4. That's going to be my b squared in the formula. So I'm going to take a 4 out of 13. So therefore I need to add 9 to complete 13. So basically you add to 4x, to the middle term, exactly the term that completes the formula a squared plus 2ab plus b squared. And when you do that, then you can combine these first three terms into x plus 2 quantity squared plus 9. So you need to do this completion of the square. And I actually, well, let me actually make a quick modification to make it even more, because this is too particular. I mean, it's too, let's make a little change here. Let's say on the top I have x plus 5, not plus 2, to make it even more general. Again, we won't deal with examples like this, but I just want to show you how the game works, basically. And by the way, you will do something similar, like I said, in differential equations when you deal with the Laplace transform, which basically entails using partial fraction decomposition for some functions that you need to handle in that chapter. Okay. So moving on, The next step would be to emphasize x plus 2 on the top, again without changing the overall value of the coefficient. So you can add 2 and subtract 2. And then break the fraction into two pieces by isolating x plus 2. So you need to keep basically x plus 2 on the top to be in the agreement with what you have under the square on the bottom. So that's the idea. You need to put this separately here. So you complete the square first, you identify what's under that square. You need to put the same term on the top by adding and subtracting a constant maybe, and keep that separated. And then the remaining fraction, 5 minus 2 was 3. And now each of these can be integrated pretty much like we did before, with slight modifications. So for example, the first integral becomes, the substitution that works there is going to be u equals x plus 2. Actually, sorry, not u equals x plus 2. U equals the whole thing. U equals x plus 2 squared plus 9. Yeah, just like before. U equals x plus 2 squared plus 9. Du equals 2 quantity x plus 2 dx. And here you could do a quick u substitution, but it's going to be just like the inverse tangent before here. So you could also do here u equals x plus 2, du equals dx. And let's see, the first term becomes 1 over u, because x plus 2 squared plus 9 is u. X plus 2 dx is du over 2. And here again, u is going to be x plus 2. Not x plus 2, is going to be, let's do actually the other substitution later. And then plus, because then I'm getting confused on my notation. Okay, so the first one becomes 1 over 2 ln of u, and ln was again u was x plus 2 squared plus 9. This one basically, x plus 2 is like x basically if you do that substitution. So you could think of this as of the same type of integral, like 1 over x squared plus a squared. So it's going to be an arctangent. So you can take the 3 out, and then it's going to be 1 over x plus 2 squared plus 9. So that ends up being 1/3 inverse tangent of x plus 2 now over 3 plus a constant c. All right, so I hope everybody is convinced that things are a little bit more complicated when you have a partial fraction of the second type. But the important thing is that we do know how to integrate them. I'm going to add one single remark about multiplicity, because believe it or not, we still didn't actually end up with the worst possible situation. Remember, you could have multiplicity on the bottom, like, that n could be 2, 3 or so on other powers than 1. So how do you, for example, let's put here as a quotation mark, how would you integrate, let's say, x minus 1 over x squared plus 9 to the power 4, let's say. So what if you have a fraction like this, which is again a type 2, but with multiplicity 4. So again, you can break it down into two pieces. You can still make a substitution in this case, like we did it before. But then the question is, for instance, what you do with the last part, let's say with 1 over x squared plus 9 to the power 4. When you end up with things like that, then you could think about trig substitutions. Basically the topic we learned on the previous lesson. So for example, here we can think about replacing x with 3 tangent of theta and perform the trigonometric substitution if something else doesn't work. But I will avoid multiplicity of irreducible quadratics because these problems tend to be too long. So you can stop for now and cover the rest of the lecture in a different sitting, but for now, just make sure you understand what a partial fraction is, type 1 and type 2, how to integrate a type 1 fraction, which is an easy job, relatively speaking, and how to integrate the easiest type of type 2 rational partial fraction, which is like this one, when you have a linear term on the top and an irreducible quadratic on the bottom of the form x squared plus a positive constant. Later on, I will avoid these cases with completion of the square and multiplicities of higher numbers than 1. So otherwise, stay tuned for the continuation of this lesson. All right, so how do we split a rational fraction into partial fractions? So there are a couple of things to talk about before I show you the main idea. Just remember the general form of a rational fraction, right? A polynomial of degree n on the top over a polynomial of degree m on the bottom. We're going to take a look at a slightly different rational fraction. So let's consider a rational fraction. Let's call actually the top p of x and the bottom q of x so I can refer to both of them faster than writing the whole thing. So the numerator is again a polynomial of degree n and on the bottom I'm going to have a polynomial of degree m but with the leading coefficient equal to 1. So x to the m plus, and let's call the other coefficients as they are before, bm minus 1, x to the m minus 1, all the way up to b1x plus b naught. So leading coefficient 1, and another very important condition, keep this in mind, the degree of p of x strictly less than the degree of q of x. So we're looking at n strictly less than m. If it's the other way around, there is a different way to handle that. It's a slight modification of the algorithm, no big deal, but we'll get to that in due course. So once again, the rational fraction we will consider in order to eventually integrate is, just like before, polynomial over polynomial, but with two additional conditions. The degree on the top is strictly less than the degree on the bottom, and the leading coefficient of the degree of the denominator is equal to 1. These type of polynomials, by the way, are called Monic polynomials when the leading coefficient is 1. It's a clever way actually to make things a little bit more streamlined for many purposes, because if you think about being too big of a restriction, because plenty of polynomials don't have the leading coefficient equal to 1, in reality actually you can make it to be 1. So if you think about it, imagine you have a starting point, your rational fraction, like I put it here on the top of the page, and imagine you divide both sides by bm. So if I divide, which is a constant, so you could do that obviously. So if I divide both sides by bm, you're going to have, of course, different coefficients on the top, right? Those will be renamed, but on the bottom you'll have the leading coefficient equal to 1. So that simplifies a little bit the notation. Also, when I explained the algorithm of how to integrate and so on and so forth. Okay, so we have this rational fraction. Now, the next thing the next step in the process is to factor q of x completely. So factor it in all possible irreducible factors. So completely, that means in irreducible factors. If you manage to do this correctly, then q of x will have only only linear terms and irreducible quadratics. So if you factor q of x completely, it will contain only factors like this. Either linear terms, let's say x plus a to the power n, right? So a linear term with some multiplicity, which can be 1, 2, 3, and so on, or an irreducible quadratic x squared plus cx plus d, again at a certain multiplicity n, which can be 1, 2, 3, and so on. So it's important to remember this should be irreducible, because if it's reducible, then you need to factor it completely. Let me give you actually a quick example so that we know what we're talking about here. So let's say q of x is equal to x squared minus let's say minus 3x plus 2. Let's put another version here. Q of x, let's say, is equal to x minus 1 squared, x squared minus 4 to the power 3, or q of x equals let's say x times x minus 1 to the power 3 times x squared plus 1. So the first one can be factored into linear terms, right? X minus 1 times x minus 2. The second one, don't be tempted to say that it's factored already, because the first term is linear, the second term is a quadratic, but it is not an irreducible quadratic, right? So the second term here can still be factored. So x squared minus 4 can be factored into x minus 2, x plus 2. And when you distribute the power, you basically end up with 3 linear terms with multiplicity 3 in this case. So of course we're going to handle by hand, examples that are not too complicated, but this is the important piece to be made here. I mean, the important remark. Okay, so it should be factored completely into irreducible factors, which can be either linear or quadratic. This is already factored, the last example, because x is linear, x minus 1 is linear, multiplicity 3, x squared plus 1 is irreducible, multiplicity 1. That's as far as you can go with the factorization. Okay, so that being said, once you actually factor this polynomial completely, there is an important theorem, basically, that states that p of x over q of x can be written as a sum of partial fractions as follows. So to each factor in q of x, to each factor of the type x plus let's say x plus b to the power n, we have the following partial fractions in the decomposition of the partial fractions. So we have a over x plus a1 over x plus b plus a2 over x plus b squared plus dot 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 a n over x plus b to the power n. So multiplicity matter. If you have x plus b to the power n in the factorization of q of x, when you split the original fraction into partial fractions for each of these factors, for x plus b to the power n, you're going to have n partial fractions of this type, each of them with all the multiplicities from 1 up to n. So for example, if the if the multiplicity was 3, like in the second example above, then you would have 3 terms. Like for example, a1 over x plus 2, a2 over x plus 2 to the power 2, a3 over x plus 2 to the power 3. All of these will be constants to be determined, which you will see later how we're going to do that. And you'll see why actually I avoid multiplicities, by the way, because, if you do this by hand, it's going to be far too tedious. But you'll see with Maple or something similar how this works out when you have to do this. And you may guess that when you have term of the irreducible quadratic, you have kind of the same idea. So to each factor of the type x squared plus cx plus d to the power n, then we have the following partial fractions. Again, all multiplicities like before. A linear term on the top over x squared plus cx plus d plus another linear term with different constants on the top over x squared plus cx plus d with multiplicity 2 all the way up to the nth term over x squared plus cx plus d to the power n. Okay, we're going to go over a couple of examples on the next page. Don't be too alarmed because of these symbols here. Lots of topics look far worse when you have to write the main idea in general terms. But in reality, for lots of examples, these decompositions are actually much simpler. What makes it complicated is the presence of irreducible quadratics. And of course, multiplicities, complicate matters far more because you have lots of partial fractions to take into account. But again, the idea is not to do this by hand, but to actually know the algorithm correctly, so you know what to expect when you do these decompositions, or when you run them with Maple, if you want, so you can check to see if it's correct. So on the next page, we're gonna show a couple of decompositions for some examples. And then finally, for some easier examples on how to actually come up with these decompositions by hand. So stay tuned. All right, so let's apply this algorithm to figure out how these fractions split into partial fractions. Again, remember, don't forget our criteria. The degree on the top should be less than the degree on the bottom. So let's see, if I look at the first example here, the degree on the top is 2. The degree on the bottom here, we could multiply the leading coefficients, right, mentally. So we have x third, if I were to expand it. So the degree on the bottom will be 5. So it fits. And according to the algorithm before, for each linear factor, again, taking into account the multiplicity, we have a bunch of partial fractions. So pay attention here and make sure you understand this. If not, just go back to the previous page and see how this compares to this example. And then maybe pause the video and try to answer ahead of time how this partial decomposition works in each of these cases. So we have a linear factor of multiplicity 1, which is x. So it will have a partial fraction of the type constant over x. By the way, I'm gonna name these constants a, b, c, d, and so on. You can name them a1, a2, a3, however you prefer. That doesn't matter. These constants will have to be determined before we can integrate. Then we have x minus 3, another linear term of multiplicity 1, right? So corresponding to x minus 3, we're gonna have another single term, which is b over x minus 3. And now notice here x plus 5 is of multiplicity 3. So it will require 3 partial fractions with all multiplicities from 1 to 3. So you will need c over x plus 5 plus d over x plus 5 to the power 2 plus e over x plus 5 to the power 3. So corresponding to that factor x plus 5 to the power 3, you need these 3 partial fractions of type 1. So if you do this by hand, it'll be pretty tedious work to find these a, b, c, d, e. We will, like I said, we're going to do easier examples by hand. But if you don't trust me that this is how the decomposition works, again, you can enter this fraction into Wolfram Alpha and simply type, partial fraction decomposition, and then you'll see all of these terms split like this. The second example, it will be, first of all, the second example, if you pay close attention, it's not factored yet completely on the bottom, because I have x squared minus 4, that can still be factored into x minus 2, x plus 2. On the other hand, x squared plus 5 cannot be factored further. Again, the degree on the top is 2, the degree on the bottom is going to be actually 8, because it's going to be x fourth. So again, the degree on the top is less, which is a necessary condition. Okay, so how do you split this? Try to answer this question yourself. So pause the video, and then think about it, and then check with me. For x minus 2 squared, we're going to have 2. So basically, this is corresponding to x minus 2 squared. Then for x plus 2 squared, we have another 2 of the same type. And now we have type 2 partial fractions for x squared plus 5, because that's irreducible. Again, we need 2 of them because the multiplicity is 2. So we need ex plus f over x squared plus 5. And finally, another one, let's say gx plus h over x squared plus 5 to the power 2. All right, so let's do now finally an example when we actually determine these constants and then we integrate. And so we're going to finish with a bunch of examples a little bit easier than what we had so far, so we can have so we can actually find these coefficients in a reasonable amount of time. So in order to find these coefficients, there is a general method that I want to show you, and this method can be, with experience and practice, we can improve it to make it a little bit faster along the way. Okay, so let's see how we do this. Suppose I need to, let's take the original problem. Let's say we have an integral, right? So let's say I want to integrate x minus 5 over x squared minus 3x plus 2. This is a rational fraction. The degree of the top is less than the degree on the bottom. So we can take it separately. We can factor the bottom. And we split it into partial fractions. And then we can go back to the integral and then hopefully find the integral after that. This is pretty much the easiest type of situation you can have. Just 2 linear factors and multiplicity is 1. So the split will be a over x minus 1 plus b over x minus 2. How do you find a and b? Because that's the question now, okay? I mean, you need to find the constants for which this is true. The theorem tells you that you can split this into partial fraction, but it doesn't tell you what the split is. You need to find it. And remember, all we're trying to do here is to basically write the same thing in a different format. So the left should be identical to the right-hand side. And that'll give you basically a way to figure out how to find a and b via a system of equations. So the first thing to do is to recombine the two terms on the right. So that means you multiply the first fraction by x minus 2, right? Just like you do the common denominator. And the second fraction by x minus 1. And then you identify the numerators. So the numerators on the left, the numerator on the left with the numerator on the right. The next step is to combine the terms on the right-hand side by the powers of x. So you write it as a polynomial in x. So you'll have to do some algebra here. Ax minus 2a plus bx minus b. Combine all the terms with respect to x. And basically you have the equality of two polynomials. So look carefully here. You have basically on the left a polynomial of degree 1 equal to a polynomial of degree 1. Actually, it doesn't matter the degree, because on the left you could have just a constant, but you could still think of it as a polynomial of degree 1, because if there is no x on the left, you could think of it as being 0 there, or 0 times x. But the idea is that a and b come from identifying the coefficients left and right. So a and b, let's write it as a remark here, are found from a system that comes from identifying the coefficients. So the coefficient of x on the left is equal to the coefficient of x on the right. That gives you one equation, a plus b equals 1. The coefficient, I mean the constant term on the left, is going to be equal to the constant term on the right, and that gives you another equation. If you set these equalities correctly, all of these coefficients, you should have as many equations as the number of constants. And then you could solve for a and b, for example, using elimination. You can multiply with some appropriate coefficients to cancel some of these terms. In this case, I'm lucky and I can just add the two. And b will cancel, so a minus 2a equals 1 minus 5, and that gives me a equals 4. And then you can go back to the other equation, plug in a for a, and that gives me b equals 1 minus 4, which is minus 3. So when we are done with the partial fraction decomposition, we can replace the original fraction with, well, the decomposition we just found. So a over x minus 1 is going to be 4 over x minus 1. B is minus 3, so that's minus 3 over x minus 2. And then, of course, after that, we integrate term by term. And in this simple case, with just linear terms, it's just going to be a bunch of natural logs. So 4 ln of x minus 1 minus 3 ln of x minus 2 plus a constant c. So before we move on to other examples, because we need to do obviously several of them to see various situations, I want to point out again some of the little pitfalls that can come up in problems like this. People sometimes get confused on this step when we extract the equations. So remember, all you do when you combine the partial fractions on the right, all you do, you try to write the numerators, the same numerator in a different form. So what is on the left, x minus 5, should be identical to what's on the right. So stands the reason that, for any x by the way, stands the reason that all coefficients should match. You match the coefficients left and right. And each matching gives you basically one equation. A plus b, 1, minus 2a minus b, minus 5. So my next example will be similar to this one, but I want to show you a slightly different way of coming up with these equations, which sometimes it works faster, although this matching of the coefficients is the one that works in general. But you could do a different one by essentially plugging in convenient values for x, which might speed up the process in some situations. So stay tuned for other examples. All right, so how do we do this one now? Again, similar to the previous one. Degree on the top is 0. It's just a constant. Degree on the bottom is 2. So this should split into two linear, two type 1 partial fractions, like this. Okay, so I want to find a and b by the previous method, and then I'm going to show you the trick I mentioned late after that, a faster way to find a and b. So recombine, just like before, the two fractions. The first one is multiplied by x minus 1, the second one by x plus 2. Then we match 3 with ax minus 1 plus bx plus 2. Again, on the right hand side, you expand and collect the terms by the powers of x, so a plus bx minus a plus 2b. And again, this is another case when people get confused sometimes. So what are the matching coefficients? So here we have a, let's write this one first. So we have a plus b times x, so a constant times x, minus a plus 2b, which is another constant. So constant times x plus another constant equal to 3. There is no x on the right-hand side or on the original left-hand side. But any missing coefficient, for example, there is x on the left, but there is no x on the right, that's like saying the coefficient of x on the right is 0. So basically, if I have a coefficient of x on the left, or x squared, whatever, and there is no x on the right, that's another way of saying that coefficient should be 0. So you still have a matching equation from that coefficient, but the only difference is that it's going to be equal to 0. The constant term is going to be 3. Again, we can add the two equations, and that cancels, a will cancel, so then I have 3b equals 3, b equals 1, and then I can go back to the original, to the first equation, and I can plug in 1 for b, and that gives me a equals minus 1. So a is minus 1, I'm going to have minus 1 over x plus 2, and then b is 1. So the partial fraction decomposition is going to be minus 1 over x plus 2 plus 1 over x minus 1. Now, I did mention a faster way to come about with these coefficients. So when you have linear terms, that's my advice to you basically. So let's go back to the original matching equations. And this is optional, by the way, because matching the coefficients by the power of x, again, that works in all cases. But if you have linear terms, you can actually find these coefficients faster by plugging in the plugging in for x the values that cancel these factors or these terms. Because remember, this equality should be for any x. It should be an identity. So it should work for any x. And in particular, if I plug in x equals 1, that allows me to quickly find the other coefficient, b in this case. Because if I plug in x equals 1, the first factor cancels. So I can quickly have 3 equals 3b, b equals 1. And then I can go back to the original and I can plug in the other term that cancels the other term, right? I mean, the value that cancels the other parenthesis here. So x equals minus 2. So if I plug in minus 2 for x, that'll cancel b. So I end up with 3 equals minus 3a, and then a equals minus 1. So that's a little bit faster, and it's worth doing it if you have linear terms. And then just to finish the integral, I mean, if the question was to integrate, obviously just like before, this will be a combination of two logarithms. So it's minus ln of x plus 2, kind of messy here, plus ln of x minus 1 plus a constant c. So probably let's do another, because I have this room on this page before I move on to examples containing type 2 fractions. This is optional, but it's very useful in life, to be honest with you, because I meet this before often, and I'm going to leave it as a homework to check. But basically, whenever you have, you can actually memorize this if you prefer. Basically, if you have a partial fraction like this, one on the top and two linear terms on the bottom, the decomposition is always 1 over, so let's say a is less than b. It's going to be 1 over b minus a, 1 over x plus a minus 1 over x plus b. The easiest version of this is if you have consecutive factors. So if I have 1 over x plus 1 times x plus 2, so whenever you have basically linear factors that are consecutive, so the difference between them is 1, the decomposition is always 1 over the smaller minus 1 over the bigger one. Again, this is optional, but I found it in many applications to be practical because it saves me the time to actually go through the finding the coefficients. So as a homework or as a practice, because that's not homework, right? As a practice, you can check, for example, this one to see if I'm right. So the coefficients are always opposite to each other, 1 minus 1 or whatever the difference between a and b is. So that might be worthwhile to just memorize if you prefer. So with that in mind, let's move on to another set of examples, like I said, involving partial fractions of the second type. More fun to come. All right, so let's get ready. We have a linear term of multiplicity 2, x squared. So that means a over x plus b over x squared. It's going to be the corresponding part in the partial fraction decomposition. And we have an irreducible quadratic. So this with multiplicity 1, right? So this becomes, leads to another partial fraction of type 2. Remember, that's going to be a linear term on the top over x squared plus 4 on the bottom. So believe it or not, this won't be actually really that bad. It's tedious, but not that bad as it can be, because often, even though you have in fact here 4 terms to compute, 4 constants, you will see the system will not be actually that difficult. But the algebra, until you get to that system, yes, it is tedious, so you have to be patient. How do we remember? We need to combine the fractions now, just like before, the fractions on the right hand side. So the common denominator is x squared times x squared plus 4. Be careful to multiply each fraction by the missing factor. So that means a gets to be, it has already x on the bottom, so it needs to receive another x, and x squared plus 4. B needs to be multiplied by x squared plus 4. And then cx plus d needs to be multiplied by x squared. Right, the missing factor. All right, so let's start actually with the right-hand side, because maybe it's going to be easier to set up the system. So the right-hand side, the numerator on the right-hand side, and let's do some algebra already, okay? So we have a x third. We just eliminate those parentheses. Ax third plus 4ax plus bx squared plus 4b plus cx third plus dx squared. These needs to be identical, equal to minus x third plus x squared minus 4x plus 8. Now on the left, collect the terms according to the powers of x. So a plus c, quantity x third. X squared appears in 2 positions, b plus d x squared. 4ax is by itself. That's going to be very good. You'll see that makes things much easier when you solve for a, b, c, and d. And then the constant 4b by itself. All right, matching the coefficients. A plus c should be minus 1, b plus d should be 1, 4a should be minus 4, so you can find a right away. 4b should be 8. That'll give you b right away. So you can be lucky in that way, in the sense that this system that results from this can be solved easily because some of the equations already give you the constants. So let's write the equations. A plus c equals minus 1. B plus D equals 1, 4A equals minus 4, 4B equals 8. Don't forget to catch up, pause and catch up the in order to do the computation yourself. So I can tell immediately that a is minus 1 from the third equation and b equals 2. I can just substitute then. Now, so I have minus 1 plus c equals minus 1. That gives me c equals 0. And then b plus d becomes 2 plus d equals 1. D equals minus 1. So let's say I wanted to integrate this big fraction. Then the fraction splits into a over x, that was minus 1 over x, b over x squared, that's 2 over x squared, cx plus d, because c was 0, there's only d left, and d is minus 1, so that's minus 1 over x squared plus 4. The first one is a natural log, then 2 over x squared, it's like 2 to the x to the minus 2, that's x to the negative 1 over negative 1, that's minus 2 over x. In the integral, right? Minus 2 over x, and then this one is an arctangent, so it's minus 1/2 inverse tangent of x over 2. Plus a constant c. All right, so let's do another one like this. And it would be a good idea maybe to actually do it on your own. Pause the video and do it on your own and then check the answer with me. So 5x squared minus 3x plus 13 over x minus 1 over x squared plus 4. All right, so this one has a linear term and a quadratic, both with multiplicity 1. So we just need a type 1 partial fraction plus a type 2 partial fraction. All right, so let's do the combination again. Ax squared plus 4 plus x minus 1 bx plus c. And now match the numerator. Let's expand. Ax squared plus 4a bx squared plus cx minus bx minus c and now let's combine the coefficients. We have a plus b x squared, c minus bx, 4a minus c. This is equal to 5x squared minus 3x plus 13. Okay, so what is the system then that gives me a, b, and c? Well, a plus b should be equal to 5. C minus b should be equal to minus 3. 4a minus c should be equal to 13. When you have a system like this, try to look carefully and see if you can actually find these coefficients quickly. I mean, in other words, try to find a method that doesn't take too much time. Always look for elimination. Just use the elimination method. Don't do the substitution, because that often is more tedious. And take advantage of already existing opposite terms. Like for instance, here I can just add again the first two, and that gives me a plus c equals 2. So it eliminates b, and lucky me, the third equation already has b outside of it. I mean, like, there's no b on the third equation, so I can just end up with two equations in a and c. And again, I can add the two, and then 5a equals 15. Now, if you don't have cancellations like that, again, you have to do some multiplication of convenient coefficients, so you can do the elimination yourself. So a will be 3. Going back to a plus c equals 2. That gives me c equals minus 1. And going back to the middle one, for instance, c minus b equals minus 3. That gives me b equals minus 1 plus 3, which is 2. Okay, so if I were to integrate that fraction, that integral now splits into the integral of a over x minus 1 plus bx, which is 2x minus 1 over x squared plus 4. Now remember, when we integrate this, we're gonna have to split this further because you need to, you have that u substitution with x on the top. So remember how we integrated a type 2 partial fraction. So that splits into 2x over x squared plus 4 minus 1 over x squared plus 4. So you could do this separately and then check the answer after that. But remember, this is a natural log. This is also a natural log, but via a u substitution. You take u to be x squared plus 4. And the last one is an arctangent. So take your time to actually do this slower if you want. But the answer should be 3 ln of x minus 1 plus ln of x squared plus 4. And then minus 1/2 inverse tangent of x over 2. Okay, so I hope you actually didn't do this in one sitting because it can be quite tiresome. But whether you did it or not, do you think we're done? No, we're not. There's more. I'm not going to spend too much time on this, but there is still, I'm curious if you guys actually remember at this stage, there is still one case that we still didn't discuss. Remember, the goal was to integrate any rational fraction. And up until this point, we still are under a restriction which we made from the beginning. So in case you forgot, the restriction was the degree of the numerator should be less than the degree of the denominator. So what do we do if the degree on the top is greater than or equal to the degree on the bottom? So the fix is really simple. One, perform long division, and the remainder of that division will always have the degree less than the denominator. That's one of the major theorems in algebra. So I'll mention this in the next page with an example. But again, in exams, I will give maybe very simple cases like that. It's still important to know because there are simple versions of this which you need to know how to perform, because otherwise you will stumble and you won't know how to go about if you don't remember the technique. So stay tuned for the last case. All right, so finally the case of a rational fraction, again let's call it p of x over q of x, but in which the degree of p of x is greater than or equal to the degree of q of x. Remember, so far we require that the degree on the numerator was strictly less than that of the denominator. So what if it's greater than or equal to the degree of the bottom? Well, this is basically the major theorem from algebra that comes from the long division, which states that if I do the long division, and if you forget how to do the algorithm, I'll show you immediately, then one can write, so if we do the long division, you're going to end up with a quotient, polynomial, and a remainder. So when you achieve this, I mean, when you compute these quotients and the remainders, then it turns out that your fraction can be written as the quotient, which is just a polynomial, and so it's easy to integrate with the power rule, plus the remainder divided by the denominator. And you're guaranteed, thanks to abstract algebra, that the degree of the remainder is strictly less than the degree of the quotient. So for this portion, one can use later partial fractions decomposition. again, if you are overwhelmed with all of these things and you will think about that, oh my God, these problems can be so huge. Remember, the goal is not to do by hand long problems. You will not see anything harder than what I showed already in these examples. But it's important to know the technique so that you know the approach which needs to be done by hand in basic, simple cases that you appear more often, because you can't rely. So let's put it this way. It's the reason why kids learn the multiplication table by heart, because we can't afford to use a calculator to compute 2 times 3. So stuff that appears very often in real life needs to be memorized if it's easy to do, or mentally, so to speak. And the equivalent of it in calculus at this level is that certain things have to be done directly on paper, because they are simple enough to do that and they appear often enough so that it's not worthwhile to rely on a computer. So let's do an example. Suppose I want to integrate x third minus 4x squared plus 8x minus 6 over x squared minus 3x. So remember, often people forget about this condition. Don't jump and do the partial fraction decomposition, because this again doesn't fit the description, right? So the degree on the top is going to be 3, and then the bottom is 3. Is 2, I'm sorry. So 3 is greater than 2, so we need to do long division. So how do we do long division? Well, everybody learned this in a certain way, and actually in my home country we used to arrange these things differently, but this is the American way, I guess. So the denominator here on the left, denominator here on the top, and the quotient will be built underneath the denominator here. So this will be the place for c of x eventually, the quotient. So at each step on the algorithm, you divide the leading coefficients. So x third over x squared is equal to x. Multiply the result by the whole denominator, x squared minus 3x, and change the signs and arrange them underneath the original numerator. So x times x squared is x third, change the sign. X times minus 3x is minus 3x squared, change the sign, plus 3x squared. Add the 2, so you will always need to have a cancellation of the leading coefficients. So minus 4 plus 3, that's minus x squared, plus 8x minus 6. And you continue with the same type of step until you end up with a degree strictly less than the degree of the denominator, which is 2 in this case. So this requires one more step, because the degree is 2 now. So minus x squared over x squared, that's going to be minus 1. Multiply minus 1 by the top, and it's going to be plus x squared minus 3x. This is going to be 5x minus 6. The algorithm stops because the degree now is less than 2, and this will be your remainder. And this will be again the quotient. All right, so that means your original fraction is equal to the quotient, x minus 1, plus the remainder, which is 5x minus 6, divided by x squared minus 3x. And actually, this one, we can take it separately and then do the partial fraction decomposition. So I'm going to actually ask you to do this on your own so that I don't waste too much time on the video here. Take a moment and factor the bottom here, right, which is x times x minus 3. This should split into 2 partial fractions of type 1, and do the work to find a and b. If you have done this correctly, okay, pause the video and do that on your own. Then the split of that fraction should be 2 over x. So a should be equal to 2 and b should be equal to 3, plus 3 over x minus 3. So at this point, one can integrate the whole thing, right? So the integral of the original fraction would be, for the portion of the quotient, that's just the power rule, x squared over 2 minus x. And then the rest of it is just like before, combination of logarithms, 2 ln of x, 3 ln of x minus 3, plus a constant c. Okay. And let me finish the lesson with a quick example when, what is the situation in which you shouldn't rely basically on computers, and why you need to basically remember what we just learned in this class so far. So I notice, along the years, right, many students sometimes stumble when they end up with examples like this. Let's say, find the integral of 5x minus 9 over x minus 2. And they try things like u substitution, which doesn't work, right? I mean, if you try u equals x minus 2, du equals dx, they don't know how to account for 5x minus 9 and so on and so forth. So this is essentially a typical example in which the value of the theory behind it is important, although, like I said, you don't do by hand complicated examples. So let's summarize with this basic example what we just learned. So what do we have here? It's a rational fraction. What do we know about rational fractions? Well, we can split them into partial fractions if the degree on the top is less than the degree on the bottom. The degree on the top is not less than the degree on the bottom. They are equal to each other. What we learn about that? We will learn that we can do the long division, and then we end up with the degree on the top less than the degree on the bottom. So in this case, the long division, it's not a big deal. It will involve just one step, as shown here. So 5x over x is 5, minus 5x minus 10, that's going to be plus 10. Remainder is 1. So you can quickly say, okay, this is going to be equal to, let's see, this is going to be equal to 5 plus the remainder on the top, 1 over x minus 2. And then from this point on, this should become a very simple problem, obviously, right? I mean, we don't deal with the whole shenanigans with partial fraction decomposition because, as it happens, this is already a partial fraction. There's nothing to decompose there, so it's quite immediate, right? So the integral is 5x plus ln of x minus 2 plus a constant c. But you need to know this theory behind it in order to not get confused on how to approach the problem. And that's the case with the vast majority of cases which you are expected to do by hand. So that concludes the lesson on partial fraction decomposition, and I'll see you next time.